Hello， 大家好。今年可能你们有些人会看过我之前做的 Agi 这个系列，能真正看懂那个系列的，全世界应该不会超过5个人吧。最近伊利亚他出来接受采访，讲了1个多小时。他讲的东西就是我去年那个系列讲的主要的结论，就是我的结论就是以现有的技术和硬件的条件 ，Agi 是没有办法做出来的。这一系列我把底层的原理，包括一些数学的东西都讲了。当然，我也不希望利用大家的恐惧去给你们讲一些科幻故事，因为这个已经偏离了事实了。伊利亚他新的这个一系列的采访，他终于说了一个很关键的东西，他就说现在要回归到研究时代。什么叫研究时代？就是说现有的这个模型，就现有的方式没有办法来达到上一个台阶，也就是他也说了 scaling law 无论你怎么扩张，应该就取不到那个效果。其实关于 scaling law 我之前也说过，我说 scaling law 并不像 CPU 这个摩尔定律这样，随着对这个晶体管它就能够算你就上升能效下降，它不是这种物理的规律。因为这个我之前也说过了，我再提一嘴哈。这个大家，因为它就是一个概念嘛，比如说有10个问题，你规模不够的时候，你覆盖得到2个问题，那这个东西你问剩下的8个问题，它都无法回答你，你就觉得东西没法用。当然，它如果能够把我们大概，比如说80%的问题都覆盖了。那你跟他聊天的时候，你就会误以为他什么都能够回答你，是吧？尤其用了就是强化学习，就是人写的答案，在训练之后呢，这个就显得就特智能，但实际上他没有智能啊。所以呢，你无论是如何对规模啊参数的规模，那他也无法上升 Agi。如果这样做的话，这个问题就非常严重，包括英伟达的卡你去堆的话也没有用。那这就大问题了。所以呢，伊利亚呢，他离开 OpenAI 之后，我估计是这大半年吧他思考之后，估计他也发现了问题。也就是说，我去年讲的东西呢，他现在大概也就看到了，因为他也看到你无论如何来 scaling 都无法达到 Agi， 或者无法到升一个高的台阶，所以呢，他就说要重新回到研究时代。我会先把他的1个多小时呢先放出来，这个有点长啊，分个3集吧。之后呢，我会就是给它切开，会逐一来去讲解，可能也得分个10几20集才能够去就是讲解，因为里面讲到的都是特别前沿，都很深的一些东西，大家应该是很难看得懂他这1个多小时里面的讲的内容以及当中的含金量。大家先去看看。
You know what's crazy? That all of this is real.
Yeah, meaning what?
Don't you think so?
Meaning what?
Like all this AI stuff and all
Like
this
it
Bay
actually
Area, yeah, that it's happened. Like, isn't it straight out of science fiction?
Yeah. Another thing that's crazy is like how normal the slow takeoff feels. The idea that we'd be investing 1% of GDP in AI, like I feel like it would have felt like a bigger deal, you know? Where right now it just feels like
We get used to things pretty fast, turns out, yeah. But also it's kind of like it's abstract. Like, what does it mean? What it means that you see it in the news,
yeah,
that such and such company announced such and such dollar amount.
right,
That's all you see.
right,
It's not really felt in any other way so far.
yeah. Should we actually begin here? I think this is an interesting discussion.
Sure.
I think your point about, well, from the average person's point of view, nothing is that different will continue being true even into the singularity.
No, I don't think so.
Okay, interesting.
So the thing which I was referring to, not feeling different, is, okay, so such and such company announced some difficult to comprehend dollar amount of investment.
Right.
I don't think anyone knows what to do with that.
Yeah.
But I think that the impact of AI is going to be felt. AI is going to be diffused through the economy. There are very strong economic forces for this. And I think the impact is going to be felt very strongly.
When do you expect that impact? I think the models seem smarter than their economic impact would imply.
Yeah, this is one of the very confusing things about the models right now. How to reconcile the fact that they are doing so well on evals.
Mm-hmm.
And you look at the evals and you go, those are pretty hard evals.
Right.
They're doing so well. But the economic impact seems to be dramatically behind.
Yes.
And it's almost like it's very difficult to make sense of how can the model, on the one hand, do these amazing things, and then on the other hand, like repeat itself twice in some situation in a kind of an example would be, let's say you use vibe coding to do something and you go to some place and then you get a bug. And then you tell the model, can you please fix the bug?
Yeah.
And the model says, oh my God, you're so right, I have a bug, let me go fix that. And it introduces a second bug.
Yeah.
And then you tell it, you have the second bug.
Right.
And it tells you, oh my God, how could I have done it? You're so right again. And brings back the first bug.
Yeah.
And you can alternate between those.
Yeah.
And it's like, how is that possible?
Yeah.
It's like, I'm not sure. But it does suggest that something strange is going on. I have two possible explanations. So here, this is the more kind of a whimsical explanation, is that maybe RL training makes the models a little bit too single-minded and narrowly focused, a little bit too, I don't know, unaware, even though it also makes them aware in some other ways. And because of this, they can't do basic things. But there is another explanation, which is back when people were doing pre-training, the question of what data to train on was answered because that answer was everything.
Yeah.
When you do pre-training, you need all the data. So you don't have to think, it's going to be this data or that data.
Yeah.
But when people do RL training, they do need to think. They say, okay, we want to have this kind of RL training for this thing and that kind of RL training for that thing. And from what I hear, all the companies have teams that just produce new RL environments and just add it to the training mix. And then the question is, well, what are those? There are so many degrees of freedom. There is such a huge variety of RL environments you could produce. And one thing you could do, and I think that's something that is done inadvertently, is that people take inspiration from the evals. You say, hey, I would love our model to do really well when we release it. I want the evals to look great. What would be RL training that could help on this task, right? I think that is something that happens, and I think it could explain a lot of what's going on. If you combine this with generalization of the models actually being inadequate, that has the potential to explain a lot of what we are seeing, this disconnect between eval performance and actual real world performance, which is something that we don't today exactly even understand what we mean by that.
I like this idea that the real reward hacking is the human researchers who are too focused on the evals. I think there's two ways to understand or to try to think about what you have just pointed out. One is, look, if it's the case that simply by becoming superhuman at a coding competition, a model will not automatically become more tasteful and exercise better judgment about how to improve your code base, well, then you should expand the suite of environments such that you're not just testing it on having the best performance in a coding competition. It should also be able to make the best kind of application for X thing or Y thing or Z thing. And another, maybe this is what you're hinting at, is to say, why should it be the case in the first place that becoming superhuman at coding competitions doesn't make you a more tasteful programmer more generally. Maybe the thing to do is not to keep stacking up the amount of environments and the diversity of environments to figure out an approach which lets you learn from one environment and improve your performance on something else.
So I have an analogy, a human analogy, which might be helpful. So even the case, let's take the case of competitive programming, since you mentioned that. And suppose you have two students. One of them decided they want to be the best competitive programmer, so they will practice 10,000 hours for that domain. Yeah. They will solve all the problems, memorize all the proof techniques, and be very, very, be very skilled at quickly and correctly implementing all the algorithms. And by doing so, they became the best, one of the best. Student number 2 thought, oh, competitive programming is cool. Maybe they practiced for 100 hours, much, much less, and they also did really well. Which one do you think is going to do better in their career later on?
The second.
Right? And I think that's basically what's going on. The models are much more like the first student, but even more, because then we say, okay, so the model should be good at competitive programming, so let's get every single competitive programming problem ever, and then let's do some data augmentation so we have even more competitive programming problems.
Yes.
And we train on that. And so now you got this great competitive programmer. And with this analogy, I think it's more intuitive. I think it's more intuitive with this analogy that, yeah, okay, so if it's so well trained, okay, it's like all the different algorithms and all the different proof techniques are like right at its fingertips. And it's more intuitive that with this level of preparation, it would not necessarily generalize to other things.
Mm. But then what is the analogy for what the second student is doing before they do the 100 hours of fine-tuning?
I think it's like they have it. I think it's the it factor.
Yeah.
Right? And like, I know, like when I was an undergrad, I remember there was a student like this that studied with me. So I know it exists.
Yeah. I think it's interesting to distinguish it from whatever pre-training does. So one way to understand what you just said about we don't have to choose the data in pre-training is to say, actually, it's not dissimilar to the 10,000 hours of practice. It's just that you get that 10,000 hours of practice for free because it's already somewhere in the pre-training distribution. But it's like, maybe you're suggesting actually, there's actually not that much generalization in pre-training. There's just so much data in pre-training. But it's like, it's not necessarily generalizing better than RL.
Like the main strength of pre-training is that there is A, so much of it.
Yeah.
And B, you don't have to think hard about what data to put into pre-training. And it's a very kind of natural data, and it does include in it a lot of what people do.
Yeah.
People's thoughts and a lot of the features of, it's like the whole world as projected by people onto text.
Yeah.
And pre-training tries to capture that using a huge amount of data. Pre-training is very difficult to reason about because it's so hard to understand the manner in which the model relies on pre-training data. And whenever the model makes a mistake, could it be because something by chance is not as supported by the pre-training data? And support by pre-training is maybe a loose term. I don't know if I can add anything more useful on this, but I don't think there is a human analog to pre-training.
Here's analogies that people have proposed for what the human analogy to pre-training is, and I'm curious to get your thoughts on why they're potentially wrong. One is to think about the first 18 or 15 or 13 years of a person's life when they aren't necessarily economically productive, but they are doing something that is making them understand the world better and so forth. And the other is to think about evolution as doing some kind of search for 3 billion years, which then results in a human lifetime instance. And then I'm curious if you think either of these are actually analogous to pre-training, or how would you think about at least what lifetime human learning is like, if not pre-training?
I think there are some similarities between both of these to pre-training, and pre-training tries to play the role of both of these. But I think there are some big differences as well. The amount of pre-training data is very, very staggering.
Yes.
And somehow a human being, after even 15 years with a tiny fraction of that pre-training data, they know much less.
Yeah.
But whatever they do know, they know much more deeply, somehow. And the mistakes, like already at that age, you would not make mistakes that our AIs make.
Yeah.
There is another thing. You might say, could it be something like evolution? And the answer is maybe. But in this case, I think evolution might actually have an edge. Like there is this, I remember reading about this case where that one thing that neuroscientists do, or rather one way in which neuroscientists can learn about the brain, is by studying people with brain damage to different parts of the brain.
Mm-hmm.
And some people have the most strange symptoms you could imagine. It's actually really, really interesting. And there was one case that comes to mind that's relevant. I read about this person who had some kind of brain damage that took out, I think, a stroke or an accident that took out his emotional processing. So he stopped feeling any emotion. And as a result of that, he still remained very articulate and he could solve little puzzles, and on tests he seemed to be just fine. But he felt no emotion. He didn't feel sad. He didn't feel angry. He didn't feel animated. And he became somehow extremely bad at making any decisions at all. It would take him hours to decide on which socks to wear, and he would make very bad financial decisions. And that's very... What does it say about the role of our built-in emotions in making us like a viable agent, essentially? And I guess to connect to your question about pre-training, it's like maybe if you are good enough at like getting everything out of pre-training, you could get that as well. But that's the kind of thing which seems, well, it may or may not be possible to get that from pre-training.
What is that? Clearly not just directly emotion. It seems like some almost value function like thing, which is telling you which decision to be made, like what the end reward for any decision should be. And you think that doesn't sort of implicitly come from...
I think it could. I'm just saying it's not 100% obvious.
Yeah. But what is that? Like, how do you think about emotions? What is the ML analogy for emotions?
It should be some kind of a value function thing.
Yeah.
But I don't think there is a great ML analogy, because right now value functions don't play a very prominent role in the things people do.
It might be worth defining for the audience what a value function is, if you want to do that.
I mean, certainly, I'll be very happy to do that. Right? So when people do reinforcement learning, the way reinforcement learning is done right now, how do people train those agents? So you have a neural net, and you give it a problem, and then you tell the model, go solve it. And the model takes maybe thousands, hundreds of thousands of actions or thoughts or something, and then it produces a solution. The solution is graded. And then the score is used to provide a training signal for every single action in your trajectory.
Mm-hmm.
So that means that if you are doing something that goes for a long time, if you're training a task that takes a long time to solve, you will do no learning at all until you came up with a proposed solution. That's how reinforcement learning is done naively. That's how O1, R1 ostensibly are done. The value function says something like, okay, look, maybe I could sometimes, not always, could tell you if you are doing well or badly. The notion of a value function is more useful in some domains than others. So for example, when you play chess and you lose a piece, I messed up. You don't need to play the whole game to know that what I just did was bad, and therefore whatever preceded it was also bad. So the value function lets you short circuit the wait until the very end. Like, let's suppose that you started to pursue some kind of let's suppose that you are doing some kind of a math thing or a programming thing, and you're trying to explore a particular solution direction. And after 1,000 steps of thinking, you concluded that this direction is unpromising. As soon as you conclude this, you could already get a reward signal 1,000 time steps previously when you decided to pursue down this path. You say, oh, next time I shouldn't pursue this path in a similar situation. long before you actually came up with the proposed solution.
This was in the DeepSeek R1 paper, is that the space of trajectories is so wide that maybe it's hard to learn a mapping from an intermediate trajectory and value. And also given that, in coding, for example, you'll have the wrong idea, then you'll go back, then you'll change something.
This sounds like such lack of faith in deep learning.
Yeah.
Sure, it might be difficult, but nothing deep learning can't do.
Yeah.
So my expectation is that value functions should be useful, and I fully expect that they will be used in the future, if not already. What was I alluding to with the person whose emotional center got damaged is more that maybe what it suggests is that the value function of humans is modulated by emotions in some important way that's hard-coded by evolution. And maybe that is important for people to be effective in the world.
That's the thing I was actually planning on asking you. There's something really interesting about emotions of the value function, which is that it's impressive that they have this much utility while still being rather simple to understand.
So I have two responses. I do agree that compared to the kind of things that we learn and the things we are talking about, the kind of as we are talking about, emotions are relatively simple. They might even be so simple that maybe you could map them out in a human understandable way. I think it would be cool to do. In terms of utility, though, I think there is a thing where, there is this complexity robustness trade-off, where complex things can be very useful, but simple things are very useful in a very broad range of situations. And so I think what one way to interpret what we are seeing is that we've got these emotions that essentially evolved mostly from our mammal ancestors, and then fine-tuned a little bit while we were hominids, just a bit. We do have a decent amount of social emotions, though, which mammals may lack. But they're not very sophisticated. And because they're not sophisticated, they serve us so well in this very different world compared to the one that we've been living in. Actually, they also make mistakes. For example, our emotions, I don't know, does hunger count as an emotion? It's debatable, but I think, for example, our intuitive feeling of hunger is not succeeding in guiding us correctly in this world with an abundance of food.
Yeah. People have been talking about scaling data, scaling parameters, scaling compute. Is there a more general way to think about scaling? What are the other scaling axes?
So here is a perspective. Here's a perspective that I think might be true. So the way ML used to work is that people would just tinker with stuff and try to get interesting results. That's what's been going on in the past. Then the scaling insight arrived, right? Scaling laws, GPT-3, and suddenly everyone realized we should scale. And it's just this is an example of how language affects thought. Scaling is just one word, but it's such a powerful word because it informs people what to do. They say, okay, let's try to scale things. And so you say, okay, so what are we scaling? And pre-training was the thing to scale. It was a particular scaling recipe.
Yes.
The big breakthrough of pre-training is the realization that this recipe is good. So you say, hey, if you mix some compute with some data into a neural net of a certain size, you will get results. And you will know that it will be better if you just scale the recipe up. And this is also great. Companies love this because it gives you a very low-risk way of investing your resources. Yeah. Right? It's much harder to invest your resources in research. Compare that. If you research, you need to have go forth researchers and research and come up with something versus get more data, get more compute, you'll get something from pre-training. And indeed, it looks like based on various things some people say on Twitter, maybe it appears that Gemini have found a way to get more out of pre-training. At some point, though, pre-training will run out of data. The data is very clearly finite. And so then, okay, what do you do next? Either you do some kind of a souped up pre-training, different recipe from the one we've done before, or you're doing RL, or maybe something else. But now that compute is now very big, in some sense, we are back to the age of research. So maybe here's another way to put it. Up until 2020, from 2012 to 2020, it was the age of research. Now, from 2020 to 2025, it was the age of scaling, or maybe plus minus. Let's add error bars to those years, because people say, this is amazing, you got to scale more, keep scaling, the one word, scaling. But now the scale is so big, like, is the belief really that, oh, it's so big, but if you had 100x more, everything would be so different? Like, it would be different for sure. But like, is the belief that if you just 100x the scale, everything would be transformed? I don't think that's true. So it's back to the age of research again, just with big computers.
That's a very interesting way to put it. But let me ask you the question you just posed then. What are we scaling, and what would it mean to have a recipe? Because I guess I'm not aware of a very clean relationship that almost looks like a law of physics, which existed in pre-training. There was a power law between data or computer parameters and loss. What is the kind of relationship we should be seeking, and how should we think about what this new recipe might look like?
So we've already witnessed a transition from one type of scaling to a different type of scaling, from pre-training to RL. Now people are scaling RL. Now, based on what people say on Twitter, they spend more compute on RL than on pre-training at this point, because RL can actually consume quite a bit of compute.
Yeah.
You do very, very long rollouts.
Yes.
So it takes a lot of compute to produce those rollouts. And then you get relatively small amount of learning per rollout. So you really can spend a lot of compute. And I could imagine, like, I wouldn't at this stage, it's more like, I wouldn't even call it a scaling. I would say, hey, like, what are you doing? And is the thing you are doing the most productive thing you could be doing?
Yeah.
Can you find a more productive way of using your compute? We've discussed the value function business earlier. And maybe once people get good at value functions, they will be using their resources more productively. And if you find a whole other way of training models, you could say, is this scaling or is it just using your resources? I think it becomes a little bit ambiguous, in a sense that when people were in the age of research, back then it was like people say, hey, let's try this and this and this. Let's try that and that and that. Oh, look, something interesting is happening. And I think there will be a return to that.
So if we're back in the era of research, stepping back, what is the part of the recipe that we need to think most about? When you say value function, people are already trying the current recipe, but then having LLM as a judge and so forth. You could say that's a value function, but it sounds like you have something much more fundamental in mind. Do we need to go back to, should we even rethink pre-training at all and not just add more steps to the end of that process?
Yeah. So the discussion about value function, I think it was interesting. I want to emphasize that I think the value function is something like, it's going to make RL more efficient. And I think that makes a difference. But I think that anything you can do with a value function, you can do without, just more slowly.
Mm-hmm.
The thing which I think is the most fundamental is that these models somehow just generalize dramatically worse than people.
Yes.
And it's super obvious. That seems like a very fundamental thing.
Okay. So this is the crux, generalization. And there's two sub-questions. There's one which is about sample efficiency, which is, why should it take so much more data for these models to learn than humans? There's a second about, even separate from the amount of data it takes, there's a question of, why is it so hard to teach the thing we want to a model than to a human? Which is to say, to a human, we don't necessarily need a verifiable reward to be able to you're probably mentoring a bunch of researchers right now, and you're, talking with them, you're showing them your code, and you're showing them how you think. And from that, they're picking up your way of thinking and how they should do research. You don't have to set like a verifiable reward for them that's like, okay, this is the next part of their curriculum, and now this is the next part of your curriculum, and oh, it was this training was unstable, and there's not this schleppy bespoke process. So perhaps these two issues are actually related in some way, but I'd be curious to explore this second thing, which feels more like continual learning, and this first thing, which feels just like sample efficiency.
Yeah. So, you could actually wonder, one possible explanation for the human sample efficiency that needs to be considered is evolution. And evolution has given us a small amount of the most useful information possible. And for things like vision, hearing, and locomotion, I think there's a pretty strong case that evolution actually has given us a lot.
Mm-hmm.
So, for example, human dexterity far exceeds, robots can become dexterous too if you subject them to like a huge amount of training and simulation. But to train a robot in the real world to quickly like pick up a new skill like a person does seems very out of reach.
Yeah.
And here you could say, oh yeah, like locomotion, all our ancestors needed great locomotion, squirrels, so locomotion maybe like we've got like some unbelievable prior.
Yeah.
You could make the same case for vision. I believe Jan LeCun made the point, children learn to drive after like 10 hours of practice, which is true. But our vision is so good. At least for me, when I remember myself being 5-year-old, I was very excited about cars back then. And I'm pretty sure my car recognition was more than adequate for self-driving already as a 5-year-old. You don't get to see that much data as a 5-year-old. You spend most of your time in your parents' house. So you have very low data diversity. Yeah. But you could say maybe that's evolution too. But then language and math and coding, probably not.
It still seems better than models. Obviously models are better than the average human at language and math and coding, but are they better at the average human at learning?
Oh yeah, absolutely. What I meant to say is that language, math, and coding, and especially math and coding, suggests that whatever it is that makes people good at learning is probably not so much a complicated prior, but something more, some fundamental thing.
Wait, I'm not sure I understood. Why should that be the case?
So consider a skill that people exhibit some kind of great reliability or,
Yeah.
If the skill is one that was very useful to our ancestors for many millions of years, hundreds of millions of years, you could argue that maybe humans are good at it because of evolution, because we have a prior, an evolutionary prior that's encoded in some very non-obvious way that somehow makes us so good at it.
Yeah.
But if people exhibit great ability, reliability, robustness, ability to learn in a domain that really did not exist until recently, then this is more an indication that people might have just better machine learning, period.